Hey, here we go again with another GCSE paper. This time it's the higher tier Combined Science Chemistry Paper 2 from June 2019. Now, we are going to go through this. I'm going to write on it and you're going to learn some things. So yay. Now, where's my little pen? There we go. Turn that thing on. So, it says, most fuels today are obtained from crude oil. Which statement about crude oil is correct? Crude oil is a compound. Oh, it's not. It's a mixture. Crude oil is a mixture of hydrocarbons. It is. Crude oil contains different hydrocarbons with the same molecular formula. Nope. Crude oil is an unlimited supply of hydrocarbons. Okay, so it's gotta be B. There we go. It's gotta be B. Now, crude oil is separated into several fractions by fractional distillation. Two of these fractions are kerosene and diesel oil. Okay, so did you learn your uses of these things? Kerosene is used for, amongst other things, kerosene is used for, amongst other things, hang on, kerosene is used, amongst other things, for planes. Okay, it's used for planes, so it's used for jet engines. Okay, so it's fuel for planes. And diesel oil, of course, is fuel for cars. Good. Now, figure 1 shows where the fractions kerosene and diesel oil are produced in a fractioning column. So there we go. It tells you there where they are produced in the column. All we have to do then is say kerosene is retained higher up in the column than diesel oil. Kerosene and diesel oil fractions have slightly different properties. Choose a property, state of this property for kerosene compares with the property for diesel oil. So, okay, you might choose to go for example, flammability. Let's just go for flammability. So flammability. Hang on. I'm wandering off here. Flammability. It's very hard to write with this pen. And of course, it gets more flammable as you go up. Brilliant. Now, it says, and I quote, figure 2 shows the formula of butane and a molecule of pentane. Butane and pentane are neighbouring members of the same homologous series. Okay. Now explain using these formulas why butane and pentane are neighbouring molecules of the same homologous series. Okay. So they have the same general formula. They're both alkanes. Okay, so the same general formula, but they differ by ACH2. That's the difference, okay? So homologous series, same general formula, they differ by a CH2. Next, it says butane has the formula C4H10. Calculate the mass of carbon in 100 grams of butane. Give your answer to 3 significant figures, then gives you the relative atomic mass of hydrogen and carbon and the atomic mass of butane as 58. Okay, now, so this is 3 marks. So to do this, the first thing I would do is you need to work out how many carbons there are. Okay, so there are 4 carbons. Okay, each one is 12. So that means we've got a mass in total of 48. Okay, so the carbons have a total atomic mass of 48. What you then do is you just do 48 divided by 58, which is the formula mass of the whole thing, and then times that by 100. Okay, and that gives us a mass of 82.8 grams. Next, it says an aluminium atom has an atomic number 13 and a mass number 27. Which row shows the number of subatomic particles present in an aluminium ion? Oh, look at that. They tried to do a sneaky on you. It's an ion. Now, what does that mean? It's a 3+ ion. So it's lost 3 electrons. Okay, so it's not A because the number of protons and electrons are the same. It can't be A. It can't be C or D because that they both have 14 protons, which doesn't equal an atomic number 13. So it has to be B. Now, if you didn't read the fact that it was an ion, you would have selected A, and you would have been wrong. Now, magnesium burns in excess oxygen to form magnesium oxide. The balanced equation is as so. Starting with 1.35 grams magnesium, calculate the maximum mass of magnesium oxide that can be formed in the reaction. Relative atomic mass is there. You must show your working. Okay. So, what do we need to do here? We need to say, okay, so there's a lovely grid for this. We've got to think of what we were told. So, we know the mass of Mg. We do. It's 1.35. Okay. We know the MR of magnesium. It's 24. Okay. Now we're looking for MgO. Just very quickly bang up my calculator app on my phone because I'm going to need this. So we know the mass. We know the MR. Can we now work out the number of moles? Yes, we can. We very simply, it's mass divided by, so moles is mass divided by MR basically. So 1.35 divided by 24, sorry, gives us a number of moles of 0.05625. Now I've written this all the way along, but it doesn't matter, okay, because this is 2 and this is 2, which means 0.05625 moles of this will form 0.05625 moles of magnesium oxide. Now, all I then need to do, okay, is multiply that by 40 to get my answer, okay? So I need to multiply that by 40 to get my answer. They're just going to... Seriously, why do I can't do this stuff? Now, so that means that is 2.25, okay? There we are. I should probably cut that out, but I'm not going to. This is just a reminder of how annoying children are. Anyway, now, so there we go. So 2.25. So your final mass of magnesium oxide is 2.25 grams. Now, you may have a different method to work that out. You may have seen a better method online. You may look at mine and think, oh, that's a nice method. Whatever. As long as you get 2.25 at the end and you can show you're working, you're all good. Now, chlorine reacts with hydrogen to form hydrogen chloride. Write the balanced equation for this reaction. Okay, so we have got Cl2 plus H2 making HCl. Okay, there we go. Now, how many chlorines? There are 2. Cl2 means 2. There's only one there, so I want a big 2 in front of that. There we go. Now, there are 2 H's and 2 H's. Sorted. That was easy enough, wasn't it? Right, so there's the whole first slab of pages done. Wow, good fun. Oh, look, the next page is really short. Let's get this done. Now, it says, sodium reacts with chlorine to form sodium chloride. The electronic configuration of the sodium atom is 281 and chlorine is 287. Give the electronic configurations of the ions formed. Just the electronic configurations. So, you need to tell me what the electronic configuration of sodium ion is. It's got 1 in the outer shell, so what's going to happen? It's going to lose 1, and therefore the electronic configuration will very simply be 2.8 because it's lost that electron. Now, what about Cl though? It's got 7. It's not going to lose 7. It is in fact going to gain 1. So that will be 288, sorry. 288, what am I thinking? So it's gained 1. It goes from 287 to 288. Brilliant. Now, carbon dioxide is one of the gases in the Earth's atmosphere. The percentage of carbon dioxide in the Earth's atmosphere has changed over time. Which row of the table shows the approximate percentage of carbon dioxide thought to be in the Earth's early atmosphere and how this percentage changed to form the composition today? Okay, so it's got the percentage of carbon dioxide in the Earth's early atmosphere. Now we know that the composition of carbon dioxide in the early atmosphere was very high, so it's not likely to be A or B. However, changing carbon dioxide to today, obviously, it's very, very low now. Therefore, the answer is, starts off at 95% and has decreased. Brilliant. The actual percentage of carbon dioxide in the Earth's atmosphere today varies. Give two factors that cause the percentage of carbon dioxide in today's atmosphere to vary. Now there are 4 marks here, so you're going to need to say a factor, then give a reason. Okay, so the first one, okay, the most obvious one here is the combustion of fossil fuels. Combustion of fossil fuels. Now you know that combustion of fossil fuels gives out CO2. Gives out CO2. Okay, so the combustion of fossil fuels gives out CO2. Okay, now we need to think of another factor now, some other factor. Now let's just go with deforestation. It's tough to write with this pen. Deforestation. Okay, now that means less photosynthesis, and that means more CO2. Brilliant. Okay, what's next? Carbon dioxide is a simple molecular covalent compound. It has a low boiling point of -78.5 degrees C. Explain why it has a low boiling point. It's simple molecular, simple covalent. Okay, so what does that mean? That means there are weak intermolecular forces. These are weak intermolecular forces, okay, which require small amount of energy to break. That's what happens, okay. I'm straight down to the next question. Don't go dribbling all over the place, but you'll be able to write much smaller than I can on these lines. Right, calculate the number of molecules in 0.11 grams of carbon dioxide. Give your result to 2 significant figures. So, what we need to do here, very simply, is we take 0.11 and we divide it by our MR of carbon dioxide, which is 44. Okay, so that gives us that. And now what that tells us is 0.0025. Okay, so that essentially is telling us the number of moles. Now we remember that of course 1 mole will have Avogadro's constant in it, but if we essentially take that 0.0025 and multiply it by 6.02 times 10 to the 23, that will tell us the number of atoms, which will equal, I'll write it down here, 1.5 times 10 to the 21, my phone says, and I'm inclined to believe it. There we are. Right, number 4. We're really powering through these questions now. Some of the elements in periodic table are metals. The electronic configuration of a metal is 2.8.3. Okay, so basically what it's asking is which group and which period is it in. So for the group, that is the number of electrons in the final outer shell, which is 3. So it's got to be C or D. Okay. And the period essentially is the number of shells. So it says 3 shells, so it's in period 3. Therefore, the answer is D. Okay, lithium, potassium, and rubidium are all metals. Describe what you would see when a small piece of rubidium is dropped into water. 2 marks. You've got to say 2 things. Now, we remember, of course, from me choking while I did it, that hydrogen gas is produced. Okay. Hydrogen gas is produced, okay? Gas is produced. However, that isn't what you would see, is it? You would see the bubbles of that gas. Got to remember that. It's what you would see. Yeah, you would see the bubbles of that gas. The gas is being produced, but you wouldn't see the gas molecules being formed. You would see the bubbles of that gas. You've got to be really clear there. Now, obviously, as you know as well, the rubidium will form rubidium oxide, and therefore the metal, the piece of metal, the piece of rubidium would get smaller. Okay, would get smaller and eventually perhaps disappear. Good stuff. Right, now the next one. The electronic configuration of lithium is 2.1. The electronic configuration of potassium is 2.8.8.1. Lithium is less reactive than potassium. Can you explain why lithium is less reactive than potassium, okay? So you've got to talk about lithium in this context. So in lithium, as we remember, okay, lithium, the outer shell electron is closer to the nucleus. It's closer to the nucleus. It is, because it's closer to the nucleus, okay? That means there is more attraction to the nucleus. So this is point number 2, attraction to the nucleus. And if it's more strongly attracted, attraction to the nucleus, and if it's more strongly attracted to the nucleus, it is therefore the electron is harder to lose because it's closer to the nucleus. Okay, so it's closer to the nucleus, there's less shielding, it's harder to lose. Okay, which means it's less reactive. Okay, brilliant. So there we are, second row of pages done. Let's cycle ourselves back over to see what joys we've got coming to us next. So it says lithium has 2 naturally occurring isotopes, lithium-6 and lithium-7. A sample of lithium contains those amounts of lithium-6 and lithium-7. I breeze over those, but we're going to need them later. Okay, calculate the relative atomic mass of lithium in this sample. Right, so how you do this, very simply, is very straightforward. So you take your, I'm going to put brackets, take your 7.59 and you multiply it by the atomic number, 6. Okay, you add that to 92.41 times 7, and then you divide all of that by 100. Okay, so what you've got is you've got basically the proportion of your 2 isotopes as a kind of percentage. So as a proportion rather. So that leads us to, let me just tap these numbers in. There's quite a complicated formula there. Let me tap these numbers into my calculator. If you're not comfortable using brackets, however, feel free to write this out down there. Okay, so let me just do that. So basically we've got 45.54. Okay, add to that, we've got 646.87. Okay, we're going to divide that by 100 with the worst line in the world, and that gives us 6.92. Remember, guys, it's not a calculator using competition, and if you're a bit unsure or not careful, just write it out in full. Nobody's going to judge you. Right, ooh, a blank page. Next, it says calcium carbonate reacts with dilute hydrochloric acid to produce calcium chloride. A student wanted to measure the amount of gas produced in 2 minutes. The student suggested this could be done by counting the number of bubbles formed. However, the bubbles are produced too quickly to count them. Figure 3 shows a conical flask where the calcium carbonate and dilute hydrochloric acid are reacting. Complete figure 3 to show the apparatus could be used to measure accurately the volume of gas given off in 2 minutes. Well, that is a perfect opportunity, isn't it, for us to use our lovely shiny gas syringe. Now make sure that's joined because obviously it's got to be tight. Maybe label it as well, gas syringe, just to show you know what you're talking about. Okay, now obviously the gas is not going to magically fly into there, so you've got to connect this up with a pipe like so, and you've got to also show there is a cork or bung in there. You could even label it. There's a bung in there to keep the gas and make it go up the pipe and into the gas syringe. Okay. Now, they don't often ask you to label these, but I think here, just chucking those 3 words on there just shows your understanding. So I don't think there's any particular downside of that. Now, the reaction between calcium carbonate and dilute hydrochloric acid is exothermic. It's explained in terms of bond making and bond breaking. Why reactions are exothermic. Now, so you know, okay, that when you break bonds, you've got to put energy in. Okay, bond breaking, therefore, if you put energy in, is endothermic. Okay, bond forming, on the other hand, on the other hand, is exothermic. Bond forming is exothermic. Now, if the reaction is overall exothermic, what that means is that energy out more than energy in. Okay, so the energy given out, more energy is given out than taken in. Okay, energy out is more than the energy taken in. There we are. Okay. Right, C. Ooh, look at this. This looks like there's going to be a lot of writing to do in this one. An investigation. It says, an investigation was carried out at the rate of reaction of calcium carbonate with dilute hydrochloric acid. 5 grams of small lumps of calcium carbonate were reacted with 50 centimeters cubed of 0.5 mole hydrochloric acid. Another 5 grams of the same size lumps of calcium carbonate were reacted with 50 centimeters cubed of 1 mole of hydrochloric acid. The volume of gas was collected and recorded. The 2 experiments were then repeated using large lumps. Now, I'll be honest with you, these questions always come up, and I like the way Edexcel do them. I do not have a lot of praise for Edexcel, I'll be honest with you, but I like the way they do them in that they put 2 things in one to give you more marks. Normally you would get a 3-mark question with only the change in concentration, but here you are changing the concentration and you are changing the surface area, and you have to talk about both, which is fantastic. Now I'm gonna try and do concentration here. Okay, I'm going to try and do concentration here, maybe use the rest of the space on the next page to do surface area. So, concentration. Let's say, what does it tell us, okay? As you double the concentration, okay, as you double the concentration, in either result, you get more gas, okay? Double the concentration in either result, you get more gas, okay? And what that means is, okay, what that means is that so more gas in, let's remember its rate, more gas in 2 minutes. Okay, so you get more gas in 2 minutes. Now, what that means is, okay, there are more particles. Okay, there are more particles if you increase the concentration with higher concentration. There are more particles. Now, if there are more particles, there is a higher frequency of collisions. Because there are more particles, there's a higher frequency of collisions. And if there's a higher frequency of collisions, okay, or more frequent collisions, basically more collisions in 2 minutes, therefore there will be a higher rate of reaction. Okay, now that's a classic 3-mark AQA kind of answer, but as I said, here they give you 2 of those to give you double the marks, which is yay. So you've written about the concentrations, you've written about this, okay, so you're going to get you're going to get 3 of the 6 marks now for just writing about concentration, but you also, ooh, look, the last set of pages, you also get this whole other load of space to write about surface area. Okay, so large lumps, okay, gave less gas in 2 minutes. I'm going to squeeze that in there. Large lumps gave less gas in 2 minutes. They did, right? Now, what does that mean? Large lumps have a smaller surface area. Large lumps have a smaller surface area. Okay, so they're all clumped together. That means there are less particles available to react. Less particles available to react. Now, if there are less particles available to react, okay, the frequency of collisions will be lower. Frequency of collisions lower. There are less frequent collisions, basically, and that means the rate is slower. Brilliant. 6 marks for that, mine. Blimey. Anyway, let's carry on now, and let's get this last question done, which is question 6. And this is it now. We are done. So, fluorine, chlorine, and bromine, and iodine, and acetylene, elements of group 7. Describe the test to show that gas is chlorine. Okay, now, you need to have learned that damp litmus paper for 1 mark, paper turns white. That's what happens to it. Damp litmus paper turns white. Bromine reacts with hydrogen to form a hydrogen bromide, which dissolves in water to form a solution. Now, you hopefully know that HCl, when it dissolves in water, forms hydrochloric acid. So hopefully it doesn't come as too much a surprise to you that this will just form hydrobromic acid. Hydrobromic acid. There is a trend in colour and the state of the halogens at room temperature. Predict the colour and state of astatine at room temperature. Now, you should know that they start off really pale green, and then of course you've got chlorine, which is pale green. You've got bromine, which is a reddy purpley browny colour. It's not purple. Iodine, which is a purple, and then so obviously it should be a very grey or black solution, very grey or black thing. And obviously it's gas, liquid, solid. So this is going to be a solid at the bottom there. Brilliant. Now, next we have our last question, our last bit of question. It says bromine, chlorine, and iodine are dissolved in water to make aqueous solutions, and potassium iodide is added to each of these solutions. It's a displacement reactions question. Yes. Now, give the observations shown in the table. So bromine, the initial colour was orange, and finally it's brown. Chlorine, the initial colour was green, and finally it's brown. And iodine, the initial colour is brown, and finally it's brown. Now, iodine or iodide is the least reactive of the halogens. Okay, what that means is it's not going to displace anything. Okay, but as a compound, it will be displaced by everything. Okay, so because chlorine and bromine are more reactive than the iodide, they will displace it. So let's just say Cl and Br more reactive than iodine. Okay, Cl and Br more reactive than iodine, therefore they will displace it. They will displace the iodide. They will displace the iodide, okay, and the brown colour is colour of iodide. Brown colour is the colour of iodine, sorry. Okay, no colour change in the last one. No colour change in the last one, as iodine will not displace iodide. What would be the point? You'll end up with the same thing. Iodine will not displace iodide. Good. Right, fluorine reacts vigorously with iron to form iron 3 fluoride FeF3. Right, so we've got iron, Fe, plus F2, making FeF3. Right, now, so let's start off, let's leave the Fe's alone because they're the same for now. Let's start off with the F. So we've got 3 and we've got 2. Now this is the trickiest balancing, I think you're likely to be asked, because what we've got to do here essentially is make them both 6 to make life easier. So to get 6 on this side, I will have 2 of those. I'll have 2 of those to have 6 on this side, and I would need 3 of those. Now I have 6 fluorines and 6 fluorines on either side, okay? But I've now got 2 FeF3s, which means I've got 2 ions as well, which means I very simply need a 2 in front of that. Job done. I'm pretty sure that's the end of the paper, apart from the periodic table, which you may or may not have needed. Well, there we go, guys. There is an exam paper gone through for you. I hope this was of some help to you. and I will be doing some more very soon. Thanks for watching.